Assalamualaikum warahmatullahi wabarakatuh. My name is Reza Putra from Mechanical Engineering KKI. And in this video, I will explain briefly about my topics. So the topics that I choose is the Laval nozzle, or usually known as convergent divergent nozzle. So we start by knowing what is the definition of the Laval nozzle. So basically, a day-level nozzle is a tube that is pinched in the middle, making a carefully balanced, asymmetric hourglass shape. It is used to accelerate a hot, pressurized gas passing through it to a higher supersonic speed in the axial thrust direction, by converting the heat energy of the flow into kinetic energy. So this is the illustration where where the gas that passing through it will get a higher supersonic speed in the axial direction. Okay, so where this type of nozzle is usually found, so this nozzle is widely used in some types of steam turbines and rocket engine nozzles. And sometimes it also can be seen in the supersonic jet engine as well. And when nozzles are needed, so nozzles are frequently needed to control the rate of flow, speed, direction, mass, shape, and or other pressure of the stream that emerges from them. In a nozzle, the velocity of fluid increases at the expense of its pressure energy. So talking about its history of who invented this type of nozzle. So in 1888, Swedish inventor Gustav de Laval created the converging diverging nozzle, or we call as the de Laval nozzle. This meant that following the reduction of flow area to a minimum, then the nozzle then expanded back outward to form an hourglass shape. This dramatically increased nozzle efficiency, allowing for far higher flow speeds at the exit. And when do we need to use this type of nozzle? So we use this type of nozzle when we are talking about an application that has something to do with supersonic jet engines and rocket engines, where higher supersonic speed gas is needed. And finally, the most important thing of this video is how does it works. So its operation relies on the different properties of gases flowing at subsonic and supersonic speeds. The speed of the subsonic flow of gas will increase if the pipe carrying it narrows because the mass flow rate is constant. The gas flow through a day-level nozzle is isentropic, where the gas entropy is nearly constant, and adiabatic, where heat loss or gain is nearly zero. At supersonic flow, the gas is compressible, so a small pressure wave will propagate through it. In the nozzle throat, while the cross-sectional area is a minimum, the gas velocity locally becomes transonic, where the Mach number is equals to 1, a condition called choked flow. As the nozzle cross-sectional area increases, the gas continues to expand and the gas flow increases to supersonic velocities where the sound wave will not propagate backwards through the gas as viewed in the rest frame of the nozzle, where Mach number has become more than 1. A day-level nozzle using a hot air at a pressure of 1000 psi or equal to 9 megapascal or 98 atm. Temperature of 1470 Kelvin will have pressure of 540 psi. Temperature of 2069 K at the throat and 15 psi. Temperature 502 K at the nozzle exit. The expansion ratio, nozzle cross-sectional area at exit divided by area at throat will be 6.8. So this is all for the explanation of my topic, my brief explanation, my introductory explanation. Thank you. Sorry if I made any mistake. Assalamualaikum warahmatullahi wabarakatuh.